Welcome to SS2 Computer Science, Term 3, Week 3. Data structures are ways of organizing and storing data in a computer's memory so that it can be accessed and modified efficiently. Choosing the right data structure for a problem is one of the most important skills in computer science. Today we study three classic linear data structures: stack, queue, and linked list. By the end of this lesson, you will define each data structure and state its key property, implement each using code and trace its operations, identify real-world applications, and answer WAEC questions on data structures. Let us begin. What is a stack? A stack is a linear data structure that follows the last in first out, LIFO, principle. The last element added to the stack is the first one to be removed. Think of a stack of plates in a cafeteria. You add a new plate to the top. When you take a plate, you take from the top. The plate at the bottom was placed first but comes out last. Stack operations: push item, add an item to the top of the stack. Pop, remove and return the item from the top. If the stack is empty, this is an underflow error. Pick /top, view the top item without removing it. Is _empty, returns true if the stack has no items. Size returns the number of items. Stack in Python using a list: stack equals an empty stack, stack.append 10, push 10, stack.append 20, push 20, stack.append 30, push 30, stack now, 30 is on top, stack.pop removes and returns 30, stack is now. Tracing: push 10, stack, push 20, stack, push 30, stack, pop, returns 30 stack, pop, returns 20 stack, pop, returns 10 stack, pop, on empty stack error, underflow. Real-world applications of stacks: function call stack. When a function calls another function, the current state is pushed onto a call stack. When the called function finishes, the state is popped back. This is how recursion works. Undo/redo in text editors: each change is pushed onto a stack. Ctrl+Z pops, undoes the last change. Browser back button: each page visited is pushed, the back button pops. Expression evaluation: checking balance parentheses, brackets, converting infix to postfix expression. Backtracking algorithms: maze solving, the current path is kept on a stack. What is a queue? A queue is a linear data structure that follows the first in first out, FIFO, principle. The first element added is the first one to be removed. Think of a queue line at a bank or ATM machine. The first person to join the line is the first to be served. New people join at the back, rear of the queue. People are served from the front. Queue operations: enqueue, item, add an item to the rear of the queue. Dequeue, remove and return the item from the front. If the queue is empty, this is an underflow error. Front/pick, view the front item without removing it. Is _empty, returns true if empty. Size, number of items. Queue in Python using a list: simple implementation: queue equals empty queue, queue.append 10, in queue 10, queue.append 20, in queue 20, queue.append 30, in queue 30, queue now, 10 is at the front, queue.pop 0, the queue from front, returns 10, queue is now. Note: queue.pop 0 on a list is slow for large queues. Use Python's collections.dig for efficient O1 dequeue operations. Tracing: enqueue 10, queue, enqueue 20, queue, enqueue 30, queue, dequeue returns 10 queue, dequeue returns 20 queue. Types of queues: simple queue, FIFO as described. Circular queue: the rear wraps around to the front when the array is full, avoids waste of space. Priority queue: items are dequeued based on priority, not arrival order. Highest priority item is served first, used in operating system scheduling. Double-ended queue: dig items can be added or removed from both front and rear. Real-world applications of queues: CPU task scheduling, processes waiting for CPU time are in a queue. Printer queues: print jobs are processed in the order they were submitted. Breadth First Search (BFS) algorithm uses a queue to explore graphs level by level. Call center systems, customer calls queued and served in order. Network packet handling, data packets in a network buffer. What is a linked list? A linked list is a linear data structure where elements, called nodes, are stored in separate memory locations and connected by pointers, links. Each node contains data, the actual value stored. Next pointer, a reference pointer to the next node in the list. The last node's next pointer is none, null. Unlike an array, the elements of a linked list are not stored in consecutive memory locations. They can be anywhere in memory, connected only by pointers. Singly linked list structure, head, a reference to the first node, traversal, start at head, follow next pointers until none. Node class in Python, class node, def__init__, self, data self.data equals data, self.next equals none. Linked list class linked list, def__init__, self.head equals none, empty list. Def append, self, data new_node equals node, data, if self.head is none, self.head equals new_node, return, current equals self.head, while current.next is not none, current equals current.next, traverse to last node, current.next equals new_node, link last node to new node. Def display, self current equals self.head, while current is not none, print, current.data, n equals current.next, print, none. Linked list operations, append, add to n traverse to last node, ORN, time, must visit all nodes. Prepend, add to front new_node.next equals self.head, self.head equals new_node, O1, time, no traversal needed. Delete a node, find the node before the one to delete, update its next pointer to skip the target node. Search, traverse the list comparing each node's data, O(n), linear time in worst case. Comparison, array versus linked list, insertion/deletion at start, linked list O1, array O(n), must shift elements. Random access, read element by index array O1, direct index, linked list O(n), must traverse from head. Memory, array, contiguous memory, linked list, scattered memory, extra memory for pointers. Dynamic size, linked list can grow/shrink easily, array fixed size, unless dynamic array/array list. Real-world applications of linked list, implementing stacks and queues internally, more memory efficient for certain operations than arrays. Music playlist, each song node has a next pointer to the next song, you can easily insert or skip songs without shifting. Browser history, doubly linked list, each node has both next and previous pointers. File allocation in operating systems, keeping track of disk blocks used by a file. Polynomial arithmetic, representing polynomials as linked list of coefficient, exponent, pairs. Comparison of the three structures, stack, LIFO, push to top, pop from top, used for function calls, undo, brackets. Queue, FIFO, enqueue to rear, dequeue from front, used for scheduling, print jobs, BFS. Linked list, dynamic size, O1, insert/delete at known position, used when frequent insertions/deletions needed, no random access. WAEC questions on data structures, define stack, queue, and linked list, state the key property of each, LIFO, FIFO, trace operations, push/pop/enqueue/dequeue/append/delete, write pseudocode or Python code for operations, give real-world examples of each, compare array with linked list, state types of queue, simple, circular, priority, dict, identify underflow and overflow in stacks and queues. Overflow, trying to push onto a full stack, when implemented with a fixed size array, underflow, trying to pop/dequeue from an empty structure. Key points, stack, LIFO, last in, first out, operations, push, pop, pick, is_empty, applications, function call stack, undo, browser back, balanced brackets. Q, FIFO, first in, first out, operations, NQ, rear, DQ, front, peak, is underscore empty, types, simple, circular, priority, DIC, applications, scheduling, printer queue, BFS. Linked list, nodes connected by pointers. Next, each node has data plus next pointer, head points to first node, singly linked versus doubly linked, both next and previous pointers, operations, append, O-N, prepend, O-1, delete, search, O-N, advantages over array, dynamic size, O-1, insert/delete at front, disadvantage, no random access. Underflow, operation on an empty structure. Overflow, operation on a full fixed size structure. Python, stack implemented with list, append/pop, queue with dic or list, append/pop, 0, linked list built with node class and pointer manipulation. WAEC, trace operations carefully step by step, no real-world applications, state LIFO and FIFO correctly, write pseudocode for operations.